Hi everyone. Today we have a pleasure to have Guillem Perarnau as our speaker from EPC Barcelona. He'll talk on extremal stationary values for directed random graphs. And Guillem, go ahead. Thank you.
Thank you very much, Liana. So first of all, I'd like to thank the organizers for organizing such a nice seminar online. So I've been attending some of the sessions and they all have been very interesting. So hopefully today it will also be. And also, yeah, thanks for inviting me to give this talk. And so the topic I want to talk about today is hopefully you will, I'll be using my iPad, and at the same time you will see me in the webcam, so it should be fine. So if you have any question, feel free to ask through the chat, because I also should be able to see the chat. So if you ask anything, I'll be able to see it probably. So let me explain you a bit what I want to talk about today. So I would like to look at the stationary distribution. So we will be talking about random walks, and this will be for directed random graph models. So this is a joint work with Xing Shi Cai from Uppsala in Sweden, and let me start introducing the model I'm going to be using. So this model is a so-called directed configuration model. And this is kind of the directed analog of the so-called configuration model. So probably you have seen the configuration model before, maybe not. So what you have is just a natural number, and then you take some degree distribution, which in this case is going to be a directed degree distribution. And you have, for each vertex, you have a number of heads and a number of tails. And then the only thing you want is to make sure that this sum is the same for each one, and I will call this number m. So what's this directed configuration model? So the only thing I'm taking is just a uniformly random perfect matching between the heads and the tails. So let me explain it by an example, because it's much simpler. So imagine that I have this degree distribution, right? So vertex 1 gets 3 heads and 1 tail, and so on. So what I'm going to do is I'm going to put 1 point for each head, not here, and 1 point here also, and I will just take a perfect matching between both sets, and then I'm going to say, well, there's an edge going out from 1 that points to 1 minus, so I have a loop here. There are 2 edges going from 2 to 1, so I have 2 edges going in this direction, and so on, right? I have one edge going from 4 to 2, which is this one here. I have a loop at 4, and I also get an edge going from 3 to 4. So from this random pairing, what I get is this random directed graph, which in particular is a multigraph, as you can see. So I have here a loop, and I can also have multiple edges. But the nice thing of this model is that if your maximum degree, and by this I'll mean the maximum in degree and the maximum out degree, are bounded by a constant, then the probability that this generates something that is simple is bounded away from 0. Meaning, and not only this, but also conditioning on this graph being simple, what you get is a uniform, simple, random directed graph. So any result that I'll be telling today that holds with high probability for this model, this directed configuration model, will also hold for simple digraph. So we will be able to transfer results to the simple setting. So hopefully the model is clear. Here I have a couple of drawings. So these are, I generated 2 of these instances. On the left-hand side, you have all the degrees between 0 and 3. And here I only displayed the largest connected component. So maybe there's some garbage around here. And in this case, you have a power law degree distribution, which means that the probability of having degree x is proportional to some polynomial of the form x to the minus alpha for some given alpha. So as you can see, depending on the degrees, what you get is something quite different. But even if they look different, they will have a lot of common properties, and that's what I would like to talk about. So as I said, like I want to study random walks on these random directed graphs. So let me start defining start defining what I understand by a random walk in a digraph. So you will have just a sequence of random variables that will take values on the vertices of your graph. And then very simple, So the probability that you will be at state B before you were at state U, I'll call this PUB. And this is just 1 over the out degree of U, if UB is an edge of your directed graph, and 0 otherwise. So it's very simple. The only thing I'm doing, I'm starting at particular vertex, right? I'm just jumping to a neighbor, jumping to a neighbor, jumping to a neighbor, maybe jumping to a neighbor, and I'm doing a random walk in this directed graph. So I'll care about the stationary distribution, and the stationary distribution is just a probability distribution that satisfies this equation. So it's this pi, where this P is the so-called transition matrix, and it's only the matrix with these entries PUB. Yeah, if there's any question, please ask. So very simple observation, if you had ever looked at random walks, then you already know that, is that if you have an undirected graph with some degree distribution, it doesn't really matter which graph do you have. The stationary distribution will always be of the form, the degree of B divided by M. And in particular, because I'm looking at the sparse graphs, this will be linear, right? This will be of order N. And also, like say, for example, the minimum degree is at least 1, and so the maximum degree is bounded. So all these values will be of order 1 over N. So in the undirected setting is very simple what you get. But for digraphs, your stationary distribution depends not only on your degrees, but also on the geometry of your graph. It depends on how your graph is. And not only this, but you even get cases where your stationary distribution is exponentially small. So here, look, like all the stationary values were of order 1 over N. Here you can get e to the minus constant N. Right? So it's very different how they do behave, and it's much more complicated to study the stationary distribution in digraphs. So let me do some remarks. So first of all, is that if your graph has a unique, strongly connected component, then your pi is also unique. Your stationary distribution is also unique, and is supported in this strongly connected component. So maybe in this case here, we have some strongly connected component that looks something like this. I don't know. There will be things that will be outside the strongly connected component, and some strongly connected component here inside. Maybe it will be even bigger, I don't know, something like this. And your pi will be supported in these values here. If your graph is itself strongly connected, then this means that you can go from any place to any place, and this is what you call an ergodic chain. So we'll have kind of these two different cases, the place where you have uniqueness and the place where you have ergodicity. And I'm going to talk about this later. And I'll be interested in the so-called extremal values. So what do I mean by extremal values? So given that pi is unique, so given that this is true, I could look at the maximum value of pi, so which is the vertex that maximizes pi, and also I can look at the minimum value of pi among all the values that are positive. Of course, I may have maybe a vertex here which is not in the strongly connected component, so its pi component is equal to 0. I don't care about this vertex. So it's good to think about this pi min and pi max in the following way. So pi, if you are in this situation where you have a unique, strongly connected component, then pi gives you so pi of b gives you the fraction of time that the random walk spends on v on the long range. So it tells you how frequent you keep visiting this vertex. So in this sense, you can think about pi max being the vertex that is visited more often by a random walk. So maybe, I don't know, I have no idea, but maybe it will be someone who is here inside. And pi min will be the one that is visited the least. So maybe it would be, I don't know, this one here. So pi max is the place where you would put like an advertisement, so everyone will see it very often. And pi min is the place where maybe you would bury your treasure so no one ever finds it. So that's, and I'm going to try to use this analogy during the talk, right? So one is the place where you will have visits more often, and the other one is the one that is hardest to visit. Why do we care about pi min and pi max? Well, they are interesting at their own, but of course, there's a lot of applications that use, in particular, pi min. So having a small pi min is important for some bounds, especially when you talk about mixing time. So for example, there's a well-known bound that relates the mixing time with the conductance, or the bottleneck ratio, also called. And it also has some term, which is depending on pi mean. So this is for non-reversible chains, which is our case. And also when you want to compare Markov chains and you want to compare the mixing time of Markov chains, you also use pi mean quite often. So in general, we care about pi mean not being too small. So not having points that are very, very difficult to reach. Is there any questions so far? Okay, so I'll continue. So, the thing I was saying was just random walks. Now I'm talking about random walks on this random graph. So there's a whole theory of random walks on random environments. And I think it's useful to think about it as having two levels of randomness. So the first thing you would sample your random graph. And after sampling this, then this would be a fixed graph. And then you would perform your random walk. So this is not really how you're going to prove the results, but it's good to think about this when defining the probability space. So what can we say in this situation? And here's where I will have these two regimes. So what's going to happen? So it's quite easy to prove that with high probability, the random walk will be ergodic if your minimum in and out degree is at least 2. Okay. Why is it so? So let me really sketch the argument. So remember that being ergodic means that you can go from everywhere to everywhere. So if you have out degree at least 2, then it turns out that with high probability, you always expand. So you always, when you look at the neighborhoods, you always grow. And when you look at the in neighborhoods, you always also grow. So these two will eventually connect and you will have a path going from X to Y. Yeah, so we call this the ergodicity regime, where you have in and out expansion. If you only have minimum degree at least 2, then what you can ensure is that you will have a unique strongly connected component. So your pi will be unique, but then you won't have this in expansion. So what's going to happen, your graph is going to look like something like some strongly connected component, which in fact will be giant. So we'll have linear size. And then you will have some towers that attach to it. You have some vertices that won't belong to the strongly connected component, but as you have minimum degree 2, everyone gets out expansion, so everyone connects to the strongly connected component. So it looks a bit like this. And I'll be talking about these two regimes, the regime where everything is well connected and the regime where everything is well connected to the strongly connected component, but not necessarily to like in the opposite direction. So what do we know about the stationary distribution on this directed random graph? So as just repeating what I said before, if your graph is undirected, then your pi is very simple and it's deterministic. It's just the degree divided by the total sum of the degrees. If the random graph is directed, then pi becomes a random measure. And the first guess maybe that you could have is, okay, so we said that pi is related to how often you reach a vertex. So maybe pi should be similar to the so-called in-degree distribution. So this is the in-degree distribution, which is just pi d minus divided by m. So maybe this is the first guess, and it won't be true, but maybe it's related.
M,
to
what was
yeah,
M? M was the number of vertices.
This m is just the sum of the degrees. So just to have a probability distribution. It just, you can say that this will be proportional to the in degrees if you want. So as I said, like this is a first guess because pi depends, well, pi is related to how often you reach a vertex. Maybe this is the answer or this is close to the answer. And there's a couple of results that support this guess. And the first one is this result from Cooper and Fries from 2012. In fact, the result is a bit more general, but what they show is that if you take an Erdős-Rényi random graph, which each directed edge is chosen independently with probability p, and your p is much larger than this log n over n, so you're above this strongly connectivity, you're in the strongly connectivity regime, so everything is well connected, then pi is essentially up to lower order terms pi 0 minus of p. So it's true that in this case, your stationary distribution behaves like the in-degree distribution. What's another result supporting this idea here? This is a much more recent result from Bordenave, Caputo, and Salez in 2018. And they say that so you are in this directed configuration model, you are in the uniqueness regime. And then it says the following. So this is a bit technical, so let me try to explain what does it mean. So this tells you, well, if you start with this distribution and you start walking, and you look at the total variation distance, which is some sort, well, I mean, if you know it, it's fine, but if you don't know it, it doesn't matter. It's just a distance between probability distributions. Then this distance here will decrease exponentially in t. So if you start, so if I give you a guy sampled from this in-degree distribution, and I let you run, your random walk, then exponentially fast I will converge to pi. So what is this saying? It's saying that maybe pi is not pi 0 minus, maybe pi is not this, maybe this is not true, but it's very close to being true. And at the same time, they give a result, which essentially says that for some distance, which is not very important in this particular case, this thing here, which is the empirical density function, which essentially controls pi, has distance to some deterministic law, which is literal law of 1. So yeah, I don't want to enter into details, but the idea is that they understand what's going on with this pi, and how is this result here. And also, this pi is not too different from this pi 0 minus. But so the only problem is that this gives us a good idea that most of the mass in this pi is close to this distribution because of this total variation distance and also about this distance. But it doesn't tell you anything about the extremal values, because extremal values there are only few of them. So they could be very widely behave, and you wouldn't see that in these distances here. Yeah,
there's a question in the chat. Fiona is asking, why is it p to the t in
thanks,
the
Fiona.
First one?
Yeah, so this t is somehow is telling you while you keep walking, you start with this distribution, and then you keep walking. And then the thing is at most rho to the t, maybe times some constant. So the more you walk, the closer and closer you get. Okay, thanks, Fiona. Yeah, I promised I would see the questions, but then I didn't. So thank you, Leanne, for pointing it out. Okay, so the message of this maybe a bit complicated statement is we understand how most of the mass is distributes, but we have no control on these small extremal values, small number of extremal values that may behave like in a very strange way. So what can we say about extremal values? So what are the extremal values? And so there's some very recent work of Caputo and Quattropani in the ergodicity regime. Remember that the ergodicity regime is when you have in and out expansion. And what they say is pi mean, so the average value of pi is of course 1 over n, because you have n of them and they have to add to 1. So from this 1 over n, the pi mean deviates at most a logarithmic amount, and the pi max also deviates at most some logarithmic amount. So you have these logarithmic fluctuations on the extremal values. Remember that for undirected graph, you always had 1 over n. So for directed graph, you have logarithmic fluctuations. What are the exponents of these logarithms? They don't manage to get exactly which is the right exponent. So these are these lambda 0, lambda 1, kappa 0. Let me talk about the zeros and not the ones. Essentially, they manage to get a very good bounds that for some distributions they match, but they still cannot control everything. So what is lambda 0 and what is kappa 0? The definition is quite simple. So for example, lambda 0 is just log of the maximum out degree divided by log of the minimum in degree. And here you have the complementary. So this in particular is larger than 1 and this is more than 1. So you have these logarithmic fluctuations. So, okay, so my goal is to try to explain you why you get this maximum and minimum degrees in this pi mean, right? So remember that, so just recall that pi mean is the most inaccessible vertex, right? So all the things I'm doing are not formal at all. So if you want to bury your treasure somewhere, what would you like? So you like two things. So imagine that my random graph is like a maze, and I'm just walking around the maze randomly. And I would like to hide something from a random walker. So what would I like to do? So first of all, I would like to put my treasure at the end of something that doesn't have many corridors leading to it. There's not many paths, not many trajectories that will lead to it, right? So I would like to minimize the trajectories that will lead to it. And what does it mean, minimize the trajectories that lead to it? It essentially means having this delta minus here, right? At each vertex. At each vertex, I would like delta minus, because delta minus is the smallest you can grow in your neighborhood. But at the same time, what I would like to imagine that you have your random walker coming here, right? And it comes like this way and wants to find the treasure. So at the same time, what I would like is that at each point, you have a lot of possibilities to make a mistake, right? That to take a bad path that will lead you somewhere else and not to my treasure. So, and because I want many possibilities to choose and only one to be good, then I have this delta plus coming in. I don't know if it makes a bit sense, this thing. So if I want to hide something, then I would like to put it at the end of a lot of vertices that satisfy this delta minus capital delta plus condition. So many branching. So it's like these two ideas. So the first one would be few corridors leading to y, or few trajectories leading to y, and the second one would be lots of branching in intersections. Is this idea clear? Because this is going to be important later. Any question? Okay, so if you look at time max, now you want to put, it's not, you are not hiding something, but you want to show something. So now it's the other way around. You want many corridors leading to it, so you get this delta minus, but you want like few branching, so you make sure that the random walk will attain this vertex y with some large probability. So that's why you get these two parameters coming into play. Hopefully it makes sense. Otherwise, please ask. I can repeat also. Okay, so what's going to happen when we drop this condition, right? Remember that we were interested in the uniqueness regime, and the uniqueness regime was only that delta plus should be at least 2. So if you drop this condition, definitely this will fail, right? Because you're going to have a problem here, because you're not going to be able to ensure in expansion. But for pi max, things will behave very similarly. So you have to believe me here that when you go from ergodicity regime to uniqueness regime, then the thing is still more or less true. And the thing that changes abruptly is this one here. Okay, so let me go to next talk. And this is precisely our result. So our result says the following. You're in the uniqueness regime, so you have these two conditions. I didn't say it explicitly, and I apologize for this. This condition is needed, otherwise it won't make sense. Well, you can weaken it a little bit, but essentially you need that. You need that your minimum degree is at least 2, because otherwise you could have vertices that take all the stationary distribution. Well, maybe later I can give more information if anyone is interested. Okay, so what does it say our result? So with high probability, your pi min is going to be of this form. So this -1 is the one that you always have, right? So the average value, remember, is 1/n. But with respect to this average value, you will have a polynomial deviation. So you will be polynomially smaller than the average value. Remember that in the previous case, I was only logarithmically smaller. Now I'm polynomially smaller. And this gamma 0 is a constant that doesn't depend on the geometry of the graph. It depends only on the degree distribution. So, and this constant is quite complicated. And the goal of the talk is just trying to explain you what's this constant. And this will be this idea of having corridors and branching. But yeah, I'll go slowly. So again, what we get is polynomial deviations with respect to this average 1 over n, and we don't control the subpolynomial terms. So we don't control logarithmic, for example, corrections or anything like this. We only control the right polynomial, the right exponent in the polynomial. Also, let me tell you that if you give me any gamma that you want, I can find a degree distribution such that this holds. So I can get things about, like, I don't know, I can get things like this. So it can be really, really bad, right? Which is completely different than in the undirected case. Remember that in the undirected case, all the terms were theta 1 over n. Why is this important? Okay, maybe I'm jumping. I'm looking at the third remark. I'm jumping the first two, then I'll come back. It turns out that timing is related very directly to the heating time. So essentially, like, because of this idea of it's the time that it takes you to access a vertex, then it may be the case that it takes you polynomially many steps for any exponent to reach a particular vertex. So there are vertices that are really, really, really hard to reach. They do not contribute on the most, like they are not most of the mass. Most of the mass is nicely behaved, but there are these vertices that are very difficult to reach. Let me also say that, as I said, pi max is nothing different than what we had before. So it's still something around 1 over n. And this comes from the result of Caputo and Quattropani. And also something nice is that you can, our proof not only gives results on pi mean, but also give results on this tail probability of the measure, meaning that for any gamma that you want between 0 and gamma 0, then you have an explicit beta such that the probability that you deviate this gamma is n to the minus beta. So it tells you how, so remember that the previous results tells you how most of the mass behave. This tells you how the tail behaves when you go to pi mean. Also, let me say here that when you put gamma equal to gamma 0, what you get is beta equal to 1. So what you're getting is when this probability is 1 over n, which is what you would be expecting because you have n vertices. Okay, so hopefully the result is clear. So typical values are of order 1 over n. And then extremal values in the ergodicity regime have logarithmic fluctuations. And in the uniqueness regime, they have polynomial deviation. So as I was saying, like, the goal for the rest of the talk is try to give you feeling of what's this gamma 0 and explaining why you get this gamma 0. No, the paper is not available yet. We should be having, in the chat there's a question if the paper is already available, and the answer is soon. So how do you want to put it?
Guillem, we lost your voice. I think it's, yeah, this is better.
Okay.
Something happens. I think you are close to your microphone speaker, maybe.
Okay, thanks, Leanne. So yeah, if there's anything that doesn't make sense, please stop me. Okay?
I had just one quick question. Could you once again mention what what were the two regimes? So this one is
the first regime is what they call ergodicity, where you have a unique. So you have a strongly connected component, which is the whole graph. You can go anywhere in your graph. Everything is strongly connected. And the uniqueness regime is when you drop the minimum degree. So there are points that don't belong to the strongly connected component. And you just have one big strongly connected component and then things attached to it. So the drawing is this one here, right? So you have this strongly connected component, and then there are things that are attached to it. So if you start random walk here, you quickly will go to here, and then you will start going around here. Okay, so how do we relate? So what are the excess probabilities? So I will denote them by pt of xy, and it's just the probability of going from x to y in t steps. So why are they useful to get pi mean? So imagine that I can prove that for every y in the strongly connected component, there exists some time such that pt xy is larger than n to the minus 1 plus gamma 0 plus little of 1 for every x in n. So this is saying that for every vertex that I can have, so for every y in my strongly connected component, which are the ones I can reach from everywhere, I can find some time. This time might depend on y, that's not a problem, and it will depend on y, such that I can reach, so the probability of reaching y from any x is large enough. So how do I continue? If I have this, then I would just say that pi y is, and this is just by the stationarity condition, is pt xy by x. And now I just use this inequality. So the sum of pi's is 1, and each of these terms is bounded from below by this quantity. So what I get is that this is at least this. So this is telling me that for any y in the strongly connected component, I have a large pi. So this is lower bounding the pi mean. Yeah, if I can access from everywhere to my y with some large probability, then I'm done with the lower bound. What about the upper bound? The upper bound is more about finding the guy who's very difficult to access. So I just need to find one in my strongly connected component, such that there exists some time also, such that the following holds. So let me define bt minus of y to be just the z's that have distance from z to y less or equal than t. So this is the ball of radius t, but in the in neighborhoods. So I'm looking at the distance from z to y. So I would like to think, so the first thing I would like is that bt is small. So say n to the little of 1, it's not too big. And the second thing I would like is that for any z in my ball, the probability of going from z to y, instead of being large, now is small. Minus 1 plus gamma 0 plus little of 1, sorry. If this is the case, then when I look at pi of y0, then I get, I mean, now this sum here, I only need to sum over this ball, because in t steps, I can only go from these elements here to y. I don't need to look outside this ball. So this is, for all the other ones, the probability should be 0. So it's the z's in my ball of pt z y pi of z. And now remember that I told you that pi max is of order n to the minus 1. So I can bound any pi of z by pi max. I don't care. So I get this n to the minus 1. And then, and here I made a mistake. This should be gamma 0. So I get this minus 1 from here. I get this minus gamma 0 from here. And I get this little of 1 from here. So at the end, I get n to the minus 1 plus gamma 0 plus little of 1. Okay, if you haven't followed the details, it's not important. So the only thing I'm trying to convince you with this is that if I control the access probabilities, then I control the minimum value of pi. So the only thing I need to show is that the access probabilities are large in some condition and are small in some other condition.
Sorry, Guillem, can you say just one more time why the probability from going from z to y is less than n to the minus alpha?
You think here?
Yeah.
Yeah, you should be thinking about, well, later it will be clear, right? But the only thing I'm saying that if I have something like this, I'm not saying that this is going to be true. So if I have
okay, sorry,
like
but
this,
you want...
then this will imply this. Yeah.
Okay.
So somehow, if I control these access probabilities, then I should be able to conclude upper and lower bounds for pi. Okay. So how I control this, and so I will try to give you some intuition of what's going on about controlling this access probability. So there's kind of two phases. One phase is departing from x. I want to go from x to y. And I want to show that essentially going from x to y will cost me n to the minus 1 minus gamma 0. So there will be a cost of departing x, and there will be a cost of landing at y. Right? And then in between, I will connect in some way. So again, it's always this idea of I go from x in this way, I go from y in the other way, and then at the middle I will connect probably. And then, so the probability of going from x to y will be the contribution of this part times the contribution of this part, if things are nice enough. So how do I depart from x? So I'll start with x. and I'll start doing my random walk. So x1, x2, x3, and so on, right? Some point, I don't know, sx minus 1, and I'll continue. And then I'm going to be looking at the following. Imagine that I look at the probability of following a particular path. I'm going to look at the expectation over all the choices for the path. So the thing now I'm going to do a lot of simplifications just to not worry about the details. And essentially, I'm going to be assuming that when I do my random walk, I'm doing a random walk in a branching process, in a Galton-Watson tree. So there's no kind of backtracking to the thing I have already visited. And every time, so no small cycles. And all the time, I'll be getting fresh, new, independent randomness. So of course, this is not the real situation, but it's good enough for getting an intuition, right? So what's the probability of following a particular path? So this will be the expectation of doing all these transitions. So transitioning from sx minus 1 to xs, from s1 to t, right? And as I'm saying, like, let me put it in red because it's not true. It's not formally true, but from the intuitive point of view, these things here behave independently. They're not independent, but if you think about branching processes, they are. So what you get is that this is the product. So I'll say like the product of the expectations of these transitions. And what's the probability of this transition? This is just 1 over the out degree of this xs minus 1. Right? So what's the probability of going from this to this? Well, you have this many out neighbors and you choose one of them. Right? So I can write this as the following. So this is exponential of minus expectation of log du plus times t. Okay, so what do I mean by this? So all these things are identically distributed because I'm in this branching process ideal situation. And they are distributed according to some distribution. I still haven't said what is this distribution. So I can just write this like this. And now I'm thinking, what about this distribution? What's the probability that a given vertex is xs, is the one that's going to be connected? So intuitively speaking, this should be related to the number of in-edges that this vertex has, right? If you have many in-edges, then you will have more probability of getting connected to a vertex. So here you have to believe me that the distribution to connect to this vertex is the so-called in-size bias distribution. So I'm biasing my initial distribution in terms of the in degree. So connecting to U has a probability of du minus over n. So if you take this into account and you put it here, then what you get is that this is the exponential minus 1 over m sum di minus log di plus times t. Okay, so hopefully convinced that the typical weight of a path that you are following has this form. So it's exponential in the length of the path, and the constant in front of the t is this expression here. This expression here, this thing here, is called h. It's normally referred to as the entropy. And this is because it can be seen as the entropy of some, the average entropy of some distribution. So what do we care? Of course, we care about when these expectations will be around 1 over n, and this is called the entropic time. So let me write it here. At entropic time, which is this log n over h, the expectation of the weight is roughly 1 over n. What does it mean? It means that, so you start with this path and you look at the weight of following this path. This is the probability of following this path. And after this entropic time, then the probability of following a particular path is 1 over n, meaning that before that, it was impossible that you were kind of well mixed, well distributed in your graph. And after that, maybe hopefully you are kind of well distributed in your graph. In fact, there's a result. So all this thing I'm explaining is it's not new. It was already known. And there's a result of Bordenave, Caputo, and Salez from 19, which says that the mixing time of this walk is roughly the entropy time, the entropic time. So somehow this should convince you that you need to at least wait for the entropic time to be well mixed, because otherwise, before the entropic time, this expectation is more than 1/n, so it's not possible that you have mixed. And what these people prove is that after that, you suddenly mix. So, okay, so the summary of this should be, it takes you this entropic time to just kind of depart from X, and after this entropic time, you are more or less well distributed among your graph. So now you need to land at Y. So you're more or less well distributed in your graph, but you still need to land to this very unlikely vertex that will attain pi mean. And this is the second part. So the first part has given us this 1/n. Now I'm going for the second part that will give us then to the minus gamma 0, and will explain us also what is this gamma 0. So here we do the same. So we want to land at Y. So we do the same, but we go in the opposite direction. Right? And so let me denote by delta, well, a partial of bt, the vertices that are really at a distance t from here. So this will be my delta bt. And let's try to think about the typical size of this set, or the expected size of this set. So now I'm going to have something very similar to what I had before. I'm going to have a vertex here. And the probability to attach to this vertex now will be related to the out degree of this vertex. So I'm going to attach with probability du plus divided by m to a particular vertex. And this is called the out size bias distribution. And this is how I'm going to be attaching to these vertices here. And each vertex that I attach will give me some new edges that will contribute to this. And how many will I have? I will have du minus of them. Right? So what's the expected increase that I will get? The expected increase, which is called nu, is just the average of this distribution. So this is this is the probability of getting a particular vertex, and this is the contribution of this vertex. So this is what we call the expansion constant. So typically, at each step, I'm going to increase a factor of nu. So the expectation of this size is going to be, well, yeah, here I forgot some things. Well, it's fine. It's going to be nu to the t. So the expectation is going to be nu to the t. This nu is in fact greater or equal than 1 by our conditions. So I expect that these things will grow, but in fact, they can also die out, and they will die out even with constant probability in most of the times. So it's not clear. Well, sorry, let me repeat it. So this is the expectation, but does it mean? But we are not looking at typical vertices. We're looking at these atypical vertices that are very hard to reach. Okay, so we want to look at the typical things, and the typical things, when you have many and different vertices, the typical things will happen. So what's the typical thing we will be looking at? The typical thing we will be looking at is that some vertex that has this bt equal to 1. So imagine that you get, right? So what we are saying is that, well, you have some y here, and then you only have one thing here. Maybe you have something different in the meantime, but at least one way you can get this. One way you can get to only have one vertex here is to have all the time. So this would be, I don't know, this du minus. So du minus should be equal to 1, right? So if you only have 1 in degree all the time, then you will have a very, very long corridor, and this vertex will be really hard to reach because there's only one corridor that leads to it. And this needs to happen for time t. So this gives you a first approximation, but it's not really the truth. And the reason is that maybe we don't have and I don't know, maybe we don't have in degree equal to 1. But in fact, if you have this condition here, you don't need to force that every vertex has degree 1, but it's enough to force that if here you have more in degree, then these branching processes, these things that you get here, will die out before time t. Right? So what you get is the following. So you want to get that there's only kind of one surviving branch that leads to y. And then maybe there's some subcritical things growing up here, but these subcritical things, they don't reach time t. At time t, you only have this guy here. And if you do this, then this allows you for much larger probability. So then you're looking at this probability that the surviving part, let me call it du star, this surviving part is equal to 1. And then this turns out to be something that is called nu hat. So we have to the t to the t. And this is kind of a subcritical behavior when you require these neighborhoods to stay small. And this nu hat is the following. So it's very related to this nu. So you can see the nu from here. So I'll have this plus di minus, and then you get some extra thing that depends on the survival probability. This is some survival probability. Well, I don't have a lot of time to explain all the details, but the idea is that because you want to grow subcritical, you get, instead of getting this thing that holds for typical expansions, you get this subcritical behavior here. So you get this nu hat. Okay, so this, remember that somehow if we want to find the place that it's hardest to access, there are two things that we need to ensure: that there are few corridors, but also that these corridors have many branchings. So about having few corridors, you have this probability here. This will tell you how these few corridors behave. And now there's the part of large branchings. And for this, I don't have that much time, but I'll try to give you some intuition. So again, you look at the expected probability to go from some z to y. So let's call z this last vertex here. And you can prove, in fact, that this is something like e to the minus h hat times t. So remember that in the first part, we prove it without the hat. We just proved that here we had the entropy. Now we have some entropy, some critical entropy, and this subcritical entropy appears from the fact that we know that this thing is subcritical. So when we're going back and we're looking for the branching things, this branching distribution is conditional on the fact that we have already explored kind of the in-degree distribution, and this was equal to 1. So what you get is a different parameter. And I'll just write it down to show you that this just has some explicit, it's not very nice, but it has some explicit form. Okay. So this has some explicit form. I don't care about the form. That only depends on the degree distribution. And this is like, you have these atypical neighborhoods that are very thin, atypical neighborhoods. And this is the typical behavior of an atypical neighborhood. But atypical neighborhoods can also behave atypically. And this is somehow the key point. So in fact, it may be the case that this probability deviates from the expectation. It matches more than the expectation. So for some alpha. And in fact, you can relate this to the so-called large deviation theory. And this is e to the minus some function that is called the large deviation rate function. And this alpha h hat times t, roughly. So the idea is that atypical neighborhoods can also behave atypically. So you have these two levels of things that are atypical. One is small neighborhoods, the other one is neighborhoods that have heavier path, heavier trajectories than what you would like. And then the final result is just a compromise between the two. It's just they have these two things that are competing. And for each distribution, you will get the right amount of each of these two properties. So you can define some function, and this function is this one here. So you define some function, and this comes from the contribution of having few corridors that lead to the treasure, and this comes from the contribution of having many branching points. And then you just minimize this. So let alpha 0 be the minimum. Alpha greater than 1 that satisfies this, or equal. And then what you get is that gamma 0 is just something explicit. Okay, so I apologize because I had to rush a bit at the end, but the message is that this gamma 0, which is the thing that was governing how unlikely is to find a point, is just a contribution of two things. How many corridors lead to this point, and how unlikely is to find the right path. So how easy is to just take another branch and disappear from the wall. And these two things compete between each other. There's times that one wins, and there's times that two wins. There's times that there's a mixture of 1 and 2. Most of the time it will be a mixture of 1 and 2. So let me put you some examples, and with this I'll finish. So this is our result, right? So what happens if your minimum degree is at least 2? Then you are in the ergodicity thing, and there's no gamma 0 appearing. So gamma 0 is equal to 0. And this is the result of Caputo and Quattropani. And they even have better results. What happens, for example, in the case where your out degree distribution is constant, right? If the out degree distribution is constant, this branching thing always behaves the same. Like every time you find a crossing, you always have R options to follow. So you don't have a typical behavior of these branching things. So the only thing that you care about is having few corridors. It's having like a very long corridor that reaches this vertex. So then this pi mean becomes related to the diameter of the graph. And in particular, you can get also an explicit form for gamma 0, which is this thing where this lambda r is just the fraction of vertices in the largest strongly connected component. And just let me say that this was already proved by Luigi Dario Berri, Borja Valle, and myself. And it's one of the motivations for this work. But in general, I can give you some very kind of silly example. For example, in this example, you have a fourth of a vertex of in degree 2 and out degree 0, a fourth with these degrees, a fourth with these degrees, and a fourth with these degrees. And then given this thing, you can compute your nu hat, you can compute your h hat, you can compute your f alpha, you can compute all these things that only depend on the degree distribution. Then you can plot your f alpha, you can find the minimum value, which in this case is this. And then you can just put it inside and get your gamma 0, which in this case would tell you that your pi mean is of the form n to the minus 2.84. And also something nice that you can see is look at this 1.84 and split it into two parts. There's the part coming from having large corridors. There's the part coming from having many branching. And for this particular distribution, this is the right amount. This is the amount that minimizes how difficult it is to find this particular vertex. I don't have any good intuition why this is 89, 11, but I just want to show you that in fact there's like for a given distribution, there's this kind of competition of these two things. And I'll finish just concluding with our theorem. And there's many open questions that we are still working on. So one is understanding pi max when your maximum degree might go to infinity. So we were always in the case where the maximum degree was bounded. So in this case, pi max doesn't change much, but if your maximum degree goes to infinity, in particular the maximum in degree, then you would hope that pi max will be much larger also. Then one can also look at the cover time. Somehow the cover time will always be essentially the heating time, and we understand the heating time, but it shouldn't be much larger than this. This is well supported by other results like Cooper and Fries and Caputo and Quattropani that prove similar results. And finally, let me say that some of the results I presented, the previous results I presented, they are in a more general setting of these sparse random Markov chains, which generalize the notion of random directed graphs. And there's many things that also hold in this more general setting, and it will be interesting to see if this extremal behavior also holds or not. And that's all. Thank you very much.
Thank you, Guillem. Let's unmute ourselves and give a round of applause.
Many thanks to all of you for coming.
So questions?
Yeah, feel free to ask any questions. So the paper should be available hopefully by the end of the month. So I'll send it to you.
Do we have any questions?
Okay. I just want to say the paper is not ready. It's mostly my fault. So Guillem has done a very good job. So the delay is on me.
Yeah, can I ask about this gamma naught? Yeah, so you're
Yeah.
saying, so can you literally get any gamma naught you want by constructing the right degree?
Yeah, I think so.
Yeah.
I think so. So you can always trickle, like kind of put a very strange degree distribution that would give you this thing to be as large as you want. It's
Yeah,
like
as large as you want, but can you?
You can always get diameter as large as you want. So
Yeah, sorry. So you can say for any constant, you can always get something bigger than that. But can you actually hit the constant or get close to it?
Oh, yeah, I guess so. I mean, yeah, I guess so.
Okay, no, cool.
Yeah,
Thanks.
just putting the right proportion should be doable. Yeah.